we are continuing our discussion on the determination of magnesium. I wanted to show you the structure of titanium. It is a fairly complicated structure, but I wanted to show it to you. It is a again triazo dye. This is sulfur group, this is nitrogen group, and then we have a double bond here followed by another aromatic ring. And again we need sulfonate groups here. O minus Na plus, and this is a CH3 group. We also have to have a similar structure on this side, that is after NH a benzene ring, that is the benzene ring, and then at the para position we have a similar structure. One is sulfur, one is nitrogen, followed by a benzene ring, again followed by SO3 Na group. This is CH3. So, this is titan yellow. So, what is important is we have this kind of organic substances that are usually present in our analytical kitty, and you can see that this structure is a fair typical of organic reagents in almost all analytical reagents. Most of them are triphenyl methane dyes, and then they will be azo dyes and then amines like that. So, the higher the molecular weight, the greater is the chromophore. So, the greater the chromophore, the better will be the colored reaction, but again it all depends upon how the organic moiety will complex with the metal ion. So, it is, as I had said earlier, it could be pH dependent also, and the complex structures, the structure of the complexes are studied by coordination chemists, and several of these metal and dye complexes, amine complexes, etc. apart from analytical uses, they also have uses as medicines and other things. So, coordination chemistry is a part of analytical chemistry, or analytical chemistry is the part of coordination chemistry, and it is very important for us to keep track of the new developments in coordination chemistry to develop new analytical reagents that can be used for chemical analysis also. So, I want you to go back to our discussion on the hydroxylamine, hydrochloride, etc. These are the reagents we have been trying to we should prepare, and as I have told you, the reaction continues to completion only around pH 12, and we add calcium as a precaution to ensure that there will not be any interference from calcium, and we have to transfer the reagents 1 to 6 ml, 10 ppm solution, and then 200 microliter of hydroxylamine hydrochloride and 200 microliter of titan yellow, etc., 1 ml of polyvinyl alcohol and 1 ml of sodium hydroxide. Now, whenever I tell you that you have to use so many microliters, you do not have to really worry about the use of micro pipettes. Basically, glass pipettes are available in for 1 ml, or so they are all calibrated with 0.1, 0.2, 0.3 ml. So, 100 microliter would be 0.1 ml. So, if I say 200 microliter, if you do not have a micro pipette, each micro pipette will cost you around 2000 rupees, or between 1000 and 2000. High end micro pipettes will also cost you around 45 to 50,000, etc. So, you do not have to really worry about whether you have a micro pipette or not. You can use ordinary glass pipettes of 1 ml calibration. There are micro pipettes are available in 1 ml, 2 ml, 5 ml, 10 ml, 25 ml, etc., glass pipettes. So, you can use them. So, you really do not have to worry about microliter when I say you can use this, unless it is 4 or 5 microliters or 10 microliter. For that sampling you may need microliters, and for that there are other ways of doing it. So, with this assurance I want to continue our discussion, and you have to prepare a calibration curve, and the calibration curve will look like this. Titan yellow, see, up to 40 ppm I have the calibration, so linear calibration. You can see that the correlation is very excellent. The linearity given by R square is 0.999, and that is a very good response. Okay, that is the recommended sample volume is 1 ml. Then cookbook value, I am recommending that you take about 40 microgram of magnesium as a standard in 10 ml, and that should give you an absorbance of about 0.365 plus or minus 0.01, that means 0.37 or 0.38, 0.34 to 0.38. If you get absorbance, you are in good hands. So, stability, the color is stable for 1 day, that means you have enough time to measure the absorbance, and Beer-Lambert's law is applicable to from 0 to 4 ppm. So, what is actually the measurement wavelength? Measurement wavelength is 554. From our knowledge of the electromagnetic radiation, we can imagine that the color would be something like magenta color, that is approximately that of potassium permanganate. Okay. So, this is the lambda max absorbance spectrum of the sample, and you can see that there is only one peak, that is against the blank, of course. Against the blank, still we have a wonderful method for the determination of magnesium. So, this figure I have already shown you, and now we move on to the determination of mercury. Now, again, mercury is one of the most dreaded element in the environment. Mercury is there everywhere. In the laboratory, yes, it is there. At homes, it is there. In hospitals it is there because doctors use mercury bulbs to measure your blood pressure, and mercury is emitted in number of industrial operations. For example, burning of coal, it contains mercury, seawater contains mercury, wherever there is, even highways, people have determined mercury from the petrochemical burning. Along the highway you can determine mercury, lot of it, and mercury is a carcinogenic. It is very well implicated in the Minamata Bay disease. I do not know how many of you have heard about the Minamata Bay disease, but mercury has been implicated. Normally mercury is present in water as inorganic mercury, methyl mercury or phenyl mercury. So, there was this company making benzaldehyde, and they somewhere around 1950s, and they used to let out the organic waste containing mercury into the sea. So, the fishes used to collect the mercury in their gills and then even in their body, and Japanese, as many of us know, are fond of seafood. They used to eat these fishes, and as a result mercury content in their body went up, and people were afflicted with neurological disorders. A lot of problems with neurology, blood pressure, etc., and it plays on the brain also if it is there in our body. So, mercury is not only implicated by Minamata Bay disease. The problems of mercury were well known even in the medieval century. In the earlier, somewhere in the medieval centuries, people used to make tall hats. If you have seen old English films, medieval English films, ladies and gents used to wear tall hats, and those hats were fitted with feathers, and the compound used to fit the feather to the hat was a mercury compound, and this mercury compound used to disintegrate and then get into the atmosphere, etc. That is one part, but the guy who prepares this hat, those guys used to ingest mercury, because mercury is having a very high vapor pressure even at room temperature. That is why we do not allow mercury to be spilled on the laboratory floor. So, even at laboratory floor, the vapor pressure of mercury is about 0.31, that is very high compared to any metal. So, we should not be breathing mercury at all, and anything that contains mercury more than even in the coal ash and other things, it is dangerous. I request all of you to be very careful with respect to mercury in your day to day life also. Doctors use mercury as a regular filler in the teeth, and that is because inorganic mercury is not so dangerous, but organic mercury is. So, that is phenyl mercury and methyl mercury, but we cannot guarantee that the mercury in our teeth or somewhere when it is used in dental caries, what is the guarantee that it will not dissolve with the food, what all we take, Coca-Cola, this, that, acid, food, acids, etc., and it may get into our system, and it used to get it will cause damage. Now, coming back to this hat business, mercury, the people who used to make the hats used to get affected by the mercury and their neurological disorders. Basically, neurological disorder means it affects the mind. Okay. So, if people go mad. So, the disease associated with mercury in the 1600 1700 AD was known as Mad Hatter's disease. So, people who used to make hats, they used to go mad, and those people used to get Mad Hatter's disease. But of course, we know now that it is the mechanisms etc. There are several thousands of applications, research publications, and then for mercury action etc. And with this introduction, I would like you to understand how to go about determination of mercury. So, normal concentration of mercury in streams is 0.07 ppm, and groundwater it varies from 0.5 to 1 ppm. It can form dimethyl mercury, which is very toxic, and a safe level of mercury in drinking water is 2 ppb, that is 0.002 ppm. So, mercury is usually not determined by spectrophotometry. We have tried to address this problem in our application in spectrophotometry, because in higher concentrations it can definitely be determined. Let us see how we are proceeding regarding the mercury. Now, what I wanted to tell you was this mercury is determined by rhodamine 6G and iodide. It forms again a ion pair complex with mercury, rhodamine 6G and iodide. It forms a ternary complex around pH 4, resulting in a color change from red to pink. The absorbance of the solution is measured around 575 nanometer, and it is proportional to the concentration of mercury. So, with this small introduction, let us look at how to go about analyzing mercury. There are several kits available for the determination of mercury even in the environment. That means, without using all these, you can use lead acetate paper. You can use lead acetate paper, and if there is mercury, mercury will form mercuric acetate, and you can coat it with dip it with sulfide solution, and mercuric sulfide will precipitate, it will give a black color. So, mercury has also got another problem, another property, basically it forms amalgams with many metals. So, whenever you are handling mercury, it is very important for you to be aware of the dangers of mercury. So, coming back to the reagents, we have the stock solution of mercury. You should not keep mercury in glass vessels. So, prepare 1000 ppm in a plastic bottle, and standard mercury working solution is 5 ppm, that is 0.5 ml of the stock solution diluted with 100 ml. Now, I think most of you are familiar with how to prepare the reagents. So, if it is a simple arithmetic involving dilutions. So, buffered iodide solution, here we have made a slight modification. What we do is we add buffer and iodide solution together. So, it is a citric acid buffer and EDTA also. So, we add about 24 gram of citric acid, 12 gram of sodium citrate, potassium iodide, and sodium thiosulfate, and 0.466 gram of disodium. That means, we are using one complexing agent, that is EDTA, followed by citric acid citrate buffer. So, adjust to pH 4 and standardize a pH meter, and you can dilute it up to 250 ml. Rhodamine 6G is again a triphenyl methane dye. I do not have to tell you what is a triphenyl methane dye now, I suppose, but still I want to give you the structure of rhodamine 6G, because I have been talking about rhodamine 6G similar structures, but still you should not get confused. Rhodamine, for example, between rhodamine B and rhodamine 6G, we have lot of similarity, because all of them are triphenyl methane dyes. Again, rhodamine 6G is a fluorescent solution, pink solution, and its structure is something like this. Then again this is also an aromatic ring, followed by NH3NCl, that is NH CH3, this should be plus, and then this is CH3 group. Then we have one more benzene ring, sort of a semi benzene ring it is. It is not here actually. How do I eliminate color? You can look up the structure in regular this is again a benzene ring, and then this is oxygen and CH3 group, and then this is CH3, and here again NH CH3. To this compound I have referred earlier in my talk on interference from about when I was talking about fluorescence, I have talked about this compound, and we can this chemical is again available across the shelf. It is again a dye which is used for dyeing the colors, dyeing the clothes. Pink, fluorescent pink color, if you see anywhere on the road, you can see that, you can imagine that it could be 99% rhodamine 6G. It is also used in the printing of notes, etc., very widely used dye. And okay, assuming that we have all those solutions, you have to prepare 1000 ppm mercury, and then 5 ppm is your working solution. Then the iodide solution, etc., I have already told. Once you have this, you prepare, add 0.1 to 2 ml of the standard mercury solution, and 10 ml of the solutions, add buffered iodide solution, followed by dilution, again adding 1 ml of rhodamine 6G, and to stabilize you have to add 0.5 ml of polyvinyl alcohol solution. So, then other things are fairly simple, that is, you have to make up to the mark and mix, measure the absorbance of the solution in 1 centimeter cuvette at 575 nanometers. You have to prepare a calibration curve as usual and refer the absorbance of the sample to the calibration curve. Now, this is the calibration curve. You can see that up to 10 microgram in 10 ml, that is 1 ppm, you should get an absorbance of about 0.03 absorbance. So, this would be the approximately 2 ppm, 2 micrograms will give you 0.1 absorbance, 0.07 or something. It is a fairly good decent number, and it will not bring you to 0.1 ppb current standards, but you will come across several situations where mercury will be in ppm level, at least ppb level. This calibration works in ppb level, parts per billion level. So, this is the absorption spectra of rhodamine 6G and buffered iodide solution with gelatin, that is A. This is the absorption, and the complex is having a lambda peak somewhere around 575, a small shoulder peak, that is a basically it is a chromophoric shift. Okay, this chromophore is extending on the, it is a bathochromic shift. So, the absorbance at this wavelength, that is around 520, goes down, and then an additional peak will, a shoulder peak will appear around 575, but around 575 the rhodamine 6G peak is almost 0, shows 0 absorbance. So, this is the difference what we are measuring around 575. So, B is the mercury solution, that is rhodamine 6G, buffered solution, gelatin or polyvinyl alcohol followed by mercury. So, recommended sample volume is about 5 ml. So, even if it contains 0.2 ppm, you should still end up with the calibration with a value of about 0.35 and 0.32 basically, but does not matter. So, 1 ppm is 0.32, 0.01 ppm is 0.03 absorbance. So, 0.03 you can measure up to 0.09, 0.1 absorbance perfectly if you take 3 ml of the solution. So, we would like to we will not say anything more about the mercury, because there are normally mercury absorption is done by hydride generation atomic absorption spectrometry. That if time permits, if I offer you one more course, I may talk to you about atomic absorption spectrometry also, but there are other methods of doing the determination of mercury with ICP, but in comparison, even though the method is not so sensitive like atomic absorption or cold vapor mercury absorption or ICP or hydride generation ICP, still the spectrophotometric method normally gives you fairly decent values using this method. We have applied this method to a number of samples, and I am very happy to tell you that this method has been developed in our laboratory, and we have applied it to several systems. So, going back, coming on to the new system, that is non-ionic surfactants, that is the next parameter of water analysis. But before that, I have to tell you about the interference of the rhodamine 6G method. So, with normally if it is extraction, you will not find many interferences, because mercury complex gets extracted and you can determine the complete the determination using the available by simple extraction, you can separate it from the matrix. But what is important is in the aqueous solution, how much it can tolerate, that gives you the value of the method. So, I am happy to tell you that lithium, magnesium, calcium, etc., alkali and alkaline metals normally do not interfere, because most of them are soluble in water and colorless. So, manganese ion, manganese, cobalt, transition metal elements, manganese, cobalt, copper, etc., they do not interfere. and at this stage I must tell you that the interference is tested around 100 ppm. That is, if we are working with about 1 ppm, the concentration of the interference will be 100 times more than that. So, all the data what I am giving you is approximately 100. That means zinc, cadmium, silver, chromium, many of these elements, arsenic, chloride, bromide, iodide, chlorate, sulphate, nitrite, silicate, phosphate, fluoride, etc., they do not interfere, including lead, antimony and cerium. So, surfactants, they do interfere because of the formation of micelles, and platinum interferes basically. Platinum and palladium, they do interfere, but chances are 99% of the time you may not be able to, you will not be getting mercury along with platinum and palladium, especially in drinking water. So, I am giving you almost a foolproof method for the determination of mercury using rhodamine 6G and iodide, and that is aqueous system. So, the whole analysis can be completed within half an hour if you have all the reagents ready with you. So, that brings me to another system, that is we will discuss about surfactants, non-ionic and ionic surfactants. Generally, in all municipal waters, especially river waters and then surface waters, ponds, etc., all of them are contaminated with surfactants nowadays. Anything that we use to wash our clothes will contain surfactant. Okay, most famously known as LAB, linear alkyl benzene, and LAB sulfonate, LABS, that is linear alkyl benzene sulfonate. There are basically 3 types of surfactants. One is cationic surfactant, another is anionic surfactant, and another is non-ionic surfactant. Okay. So, the cationic surfactants are not so much used in washing machines and soaps, etc., but anionic surfactants definitely are used, because their counterpart ion would be sodium. So, sodium sulfonate, sodium lignosulfonate, and then linear alkyl benzyl sulfonate, sodium salt. All these things are being used in surfactants. That makes them highly soluble in water, as well as they make them an essential component of all our river waters if we do not treat them. In fact, I must tell you that 99% of our water treatment problems arise from the presence of surfactants in our city municipal wastes. Whenever we take bath, we let out lot of surfactant present in our bathing soap. Whenever we wash, we let out, and 99% of the cosmetics that we use, creams and other things, moisturizers, and all those things will contain surfactants. Today, surfactant industry is one of the biggest contributor to the water problem in our industry. So, with this introduction, I want to continue our discussion on the determination of non-ionic surfactants. So, ionic surfactants, it is very easy for us to determine, and several methods are there, but non-ionic surfactants are not defined. So, all of them as a together, they can be classified as non-ionic, and we can go for the determination. So, with this introduction, I want you to take a look at this slide. Surfactants enter waters and wastewaters mainly by discharge of aqueous waste from household, industrial laundering and other cleaning operations. They are present in the range of 1 to 20 ppm even in our rivers. they interfere in the analysis of some parameters in water analysis, and the typical method is iodine iodide method. They cause a reddish turbidity with the reagent in the solution. The absorbance of the solution is measured around 500 nanometers, that means it is a red colored complex that can be measured after about 30 minutes, and the absorbance is proportional to the concentration of the surfactant. Now, most of the surfactants are represented as Triton X100. This is a very common non-ionic surfactant and available across the shelf, and it is also used in industrial samples, and you have to prepare 10 gram of that in to make up to 100 ml, that is 10%, and standard Triton you have to prepare 1000 ppm, and you need a buffer of acetic acid acetate buffer, that makes it around 4, and then we need to complex, that is EDTA 0.05 molar, and iodide iodine reagent. What you have to do is, actually it is the iodine, okay, but iodine does not dissolve in water. So, what we do is we prepare a solution of iodine in potassium iodide. That is why I have written here that you have to dissolve 1 gram of finely ground iodine and 2 gram of potassium iodide in 80 ml and dilute it up to 100 ml. And then the procedure is very simple. Nowadays, now I think most of you are familiar with the procedure, that is, you take some quantity of the standard sample, and in 10 ml add buffer, add 1 ml of EDTA, dilute to 10 ml, and then add iodine iodide solution, make up to the mark and mix. Then the complex will form. Only thing is, after the complex forms, we have to worry about how long it is stable, that will be around 30 minutes, and we have to measure a blank. So, measure against the blank also, prepare a calibration curve, very wonderful calibration curve you will get. For example, look at this complex. What is the linearity value? R square 0.998. So, up to 100 ppm we can determine very easily at 500 nanometer, that is red color, and then this is the complex 400, 450, and we are recommending 500 because it is potassium iodate iodide also has some amount of absorbance in this solution, and the cookbook value is 5 ml of the sample you can take along with your standards what we had recommended, and you can go for a cookbook value of about 40 micrograms should give you an absorbance of about 0.32 plus or minus 0.01. I think all of you must have noticed by now that most of our absorbance values are working up to are within 0.8, that is less than the relative concentration error. So, most of the time our absorbance linearity ends up around between 0.5, 0.4, 0.3 etc., but it does not mean that it ends only there. With reasonable error you can extend it up to 0.8 and up to 2 absorbance also. This we have already discussed earlier, but it depends upon the accuracy again. So, the accuracy what you achieve is something phenomenal. For example, if 40 microgram of the surfactant gives you 0.32, 10 micrograms will give you 0.08 approximately, that is 1 ppm. 1 ppm of this surfactant will give you 0.08 absorbance, a very easily determinable quantity in spectrophotometry. What you need is only a simple spectrophotometer with 350 to 750 nanometer capability. So, I have already shown you these figures, and I will not say more about these analysis, because you will find I am giving you most of the details in the course, as well as I am giving you the references, and you can look up other methods also for comparison. I taught you how to determine the how to compare the different analytical methods by means of Sandel sensitivity or the detection limit, that is approximately 0.004. So, even if you determine 3 times the standard value, that is 0.012, that itself is a great achievement. So, I hope this course will continue to give you insights into the determination of different parameters, which we will continue in our the discussion we can continue in our next classes.